Welcome to Fundamentals of Electrochemistry. Now, electrochemistry can refer to either using electrical measurements of chemical systems for analytical purposes, or using electricity to drive a chemical reaction or using a chemical reaction to produce electricity. Now let's define a redox reaction. You've probably already heard this term. A redox reaction or an oxidation-reduction reaction is a reaction involving a transfer of electrons from one chemical species to another. Now in this process, a species is oxidized when it loses electrons, and it's reduced when it gains electrons. Now the species that reduces the other is the reducing agent. And in order to reduce the other species, the reducing agent must lose its electrons to the other species and is thus oxidized in the process. On the other hand, the species that oxidizes the other is called the oxidizing agent, and in order to oxidize the other species, then the oxidizing agent must take electrons from the other species and is thus itself reduced in the process. For example, if we have this iron 3 react with this vanadium 2+ to form the iron 2+ and the vanadium 3+, then the iron here is gaining an electron to become iron 2, so it's gone from a charge of 3+ to a charge of 2+, and the vanadium has lost an electron. It's gone from a charge of 2+ to now a charge of 3+, and thus the iron 3+ is reduced to iron 2+, the vanadium 2+ is oxidized to vanadium 3+, and that means that the iron 3 is the oxidizing agent, while the vanadium 2 is the reducing agent. Now, if we perform a chemical reaction in such a way that the electrons flow through an external circuit, we can measure the current and voltage to learn about the reaction. Now, the current is proportional to the reaction rate, and the voltage is proportional to the free energy change for the reaction, that is, for delta G. Now, the electric charge, which we symbolize with a lowercase q, is measured in coulombs, which is symbolized with an uppercase C. Now, an electron has a charge of negative 1.602 times 10 to the minus 19 coulombs. So a mole of electrons has a charge of 1.602 times 10 to the minus 19 coulombs per electron times 6.022 times 10 to the 23 electrons per 1 mole of electrons. And note here that our electrons here will cancel with our electrons there, and that will give us 9.649 times 10 to the 4 coulombs per mole of electrons. Now, this value of 9.649 times 10 to the 4th coulombs per mole is what we call the Faraday constant, and we symbolize it with a capital F. We can now relate the charge transferred, Q, to the number of moles of electrons transferred, N. And so we get Q is equal to N times F, our Faraday constant. Now, suppose that 5.585 grams of iron 3 were reduced to iron 2 by our vanadium 2+. In this case, what charge must have been transferred? Well, we have our equation here. That's the same equation that we've looked at before. And we know that our charge, Q, is equal to N times F. So first we need to figure out what N is. Well, N is going to be this 5.585 grams of iron converted into moles of iron, and then converting that from moles of iron into moles of electrons. And that works out to then 0.1 moles of electrons. And we can now take that value and plug it in here in our Q equals NF. So we're taking our moles of electrons and plugging that in there. And then we're plugging in Faraday's constant here. And that gives us an answer of 9.649 times 10 to the 3 coulombs. Now current, which we symbolize with this capital I, is the charge flowing through a circuit per second and is then measured in what we call amperes. And amperes, or amps, are symbolized with this uppercase A. So 1 amp is defined to be equal to 1 coulomb per second. Now, suppose that we use electricity to drive electrons into a platinum wire in a solution containing tin 4. And that tin 4 is then reduced to tin 2+ at a rate of 4.24 millimoles per hour. What current is passing through the solution? Now note that this process cannot occur in isolation because we must balance the charge gained by the tin by an equivalent charge lost by something else, somewhere. That is, while we can separate in space oxidation and reduction portions, they must be occurring simultaneously. Also note that we call this platinum wire here an electrode. Now, platinum is a common inert electrode because it does not participate in redox reactions except as a conduit for those electrons. Now, in this case, the reduction half reaction is given here. We have our tin 4. It's gaining 2 electrons, and that's then giving us tin 2. Now, we wanted to calculate the current from our rate of reaction. And so, remember, we know that we have 4.24 millimoles of tin 4 being converted to tin 2 per hour. And we can then convert from millimoles of tin into moles of tin. So those units go away. And then we can convert from moles of tin into moles of electrons. And then we can convert our hours into minutes. So our hours will cancel. We can then convert minutes to seconds. And that then gives us a value of 2.356 times 10 to the minus 6 moles of electrons per second. And now we can convert that using Faraday's constant here into 0.227 coulombs per second, which is then 0.227 amps. Now, the difference in electrical potential, which we symbolize with this uppercase E, between 2 points is the work needed, or that can be done, when an electric charge is moved from one point to the other. Now, we measure this potential difference in volts, which we symbolize with this capital V. A decent analogy for understanding current and electrical potential is that of water flowing through a garden hose. So imagine we've turned on the tap here and we have water flowing through this reel and then coming out the end of the hose. The current is the electric charge flowing past a point in the circuit per time. And now this is analogous to the volume of water flowing past some point in the hose per unit time. So we can either look at the end of the hose, how much water comes out of the end of the hose, or say how much water is coming through our spigot over here. And so the current in both cases would be how much of our carrier, in the case of our hose here, it's how much water is spilling out the end of this hose. In the case of our electrical circuit, it's how much current is flowing through some point in that circuit per unit time. In other words, how many electrons are flowing through our circuit. Now, the electrical potential is a measure of the force pushing those electrons, the force behind those electrons. And again, this is analogous to the pressure behind the water in our garden hose. If we have greater water pressure here at our spigot, then the water is going to flow faster through our hose and come out the other end faster. Assuming, of course, that we have the same frictional resistance from the inside of this hose. Likewise, the higher the electrical potential, the larger the current flow for the same electrical resistance from the circuit. Now, when a charge Q flows through a potential difference E, the work done then is given here. We have W, our work done, is equal to E times Q. Again, E is the potential difference through which our electrons are falling, and Q is how many electrons we have, or what charges we have flowing through our circuit. Now note that work is measured in joules, which we symbolize with this capital J. And a joule is the quantity of energy gained or lost when 1 coulomb of charge moves between points whose electrical potentials differ by 1 volt. That is, 1 joule is equal to 1 volt times a coulomb. So let's calculate the work that can be done if 2.4 millimoles of electrons fall down a potential difference of 0.27 volts. Now bear in mind that this 0.27 volts is a fairly small potential difference. Remember that a single battery, a single alkaline battery, has a voltage difference of 1.5 volts, at least when it's a relatively new battery. So first we're going to convert our mole of electrons to coulombs of charge. And remember that we have Q equals NF. So first we're going to convert our millimoles of electrons into moles of electrons, and then we'll convert our moles of electrons into coulombs, and then we get 2.3 times 10 to the 2 coulombs, so 230 coulombs. And the work that can be done is then given by W equals EQ, Well, E is our potential difference, so that's this 0.27 volts. And Q is then our 2.3 times 10 to the 2 coulombs, and that gives us a value of 62 joules. Now let's go back to our garden hose example. Suppose that we raise one end of the hose 1 meter above the other and allow water to flow through a mechanical device that captures the work. And now suppose we raise one end of the hose 2 meters above the other and allow water to flow through that same mechanical device that captures the work. The work captured will double when we have our height at 2 meters here instead of only 1 meter, because the height difference through which the water has fallen will double. Now a similar effect is seen when we change the potential difference through which the electrons are falling. That is, we get twice as much work if we double the potential difference, if we double our value of E, provided of course that we keep the amount of charge transferred the same. Now the change in Gibbs energy, or Gibbs free energy, or sometimes called the free energy, for a chemical reaction conducted reversibly at constant temperature and pressure is the maximum possible electrical work that can be done by the reaction on the surroundings. That is, the work done on the surroundings, or the maximum work done on the surroundings, is equal to minus delta G. Now note that the negative sign here indicates that the free energy of the system is decreasing as energy is transferred from the system to the surroundings as work. We can now combine our definition of the change in Gibbs energy with our definition of work. That is, we have work done on the surroundings equals minus delta G, and we have W, the work done, is equal to E times Q, and remember that Q equals N times F, so if we combine all of these together, we then get delta G is equal to minus NFE. And we now have an equation relating the Gibbs energy to the electrical potential difference, E. And this means that we can now find the Gibbs energy by measuring the voltage difference produced by a chemical reaction. So now let's turn to Ohm's law. Ohm's law says that the current is directly proportional to the potential and inversely proportional to the electrical resistance, which we symbolize with this capital R, of our circuit. And we can show this in a couple of different ways. We can either show it as I, the current, is equal to E divided by R. That is, the current is equal to the electrical potential divided by the resistance of our circuit. Or we can show it this way, as E is equal to I times R. Now sometimes you'll see this written as V equals I times R. And that means exactly the same thing. We're just replacing the E here with a V instead. Now resistance is measured in ohms, which we symbolize with this Greek letter, the capital omega. Now 1 ohm is defined to be 1 volt per amp. Now power, which we symbolize with this capital P, is the work done per unit time. So if we show that mathematically, we then have P is equal to work over time. Now remember that work we have equal to E times Q, and time is then going to be symbolized with a lowercase t. And remember, Q was simply our charge, and charge over time can then be replaced with the current, because the current is simply the charge being transferred through our circuit per time. And that means that power is equal to our electrical potential difference times the current. Now the SI unit of power is the watt, which we symbolize with this capital W, and 1 watt is defined to be 1 joule per second. Now let's suppose that we have this circuit shown down here. We have a battery over here, and that battery generates a potential difference of 3 volts, and the resistance that we have over here has a resistance of 100 ohms. We're going to assume that the connecting wires up here and down here have a negligible resistance. Now note here that the electrons are flowing in a counterclockwise direction around this circuit because they're going to be repelled by the negative end of the battery, and they will then be attracted to this positive end of the battery. So in this case, the current and power produced in our circuit are given here. The current, I, remember, is equal to E over R, and that then is this 3 volts divided by our 100 ohms, and that gives us a value of 0.03 amps. And the power is then E times I, which is then our 3 volts times our 0.030 amps, and that gives us a value of 0.090 watts. Now, what happens to the power generated by the circuit? The energy is transferred from the potential energy of the battery, remember this is stored as chemical energy, and is transferred to heat in the resistor, that is, random kinetic energy of our molecules in the resistor. And then presumably if this is surrounded by air, some of that heat would then be transferred into the air in our room. Now, a galvanic cell, which is also sometimes called a voltaic cell, uses a spontaneous chemical reaction to generate electricity. Now, in this process, one reactant must be oxidized, and thus the other must be reduced. The two reactants must be separated, or the electrons will flow directly from one species to the other. Now, if we separate our reactants, such as we have down here and here, then the electrons must flow through an external circuit out here, and that then allows us to capture the energy released. We are then able to do some work with this energy. Now, we must also have a salt bridge that allows ions to balance the charge transfer via flow of electrons. Now we have our salt bridge down here, and as the electrons get transferred this direction, we then have to have either some negative charges moving through our salt bridge to balance out the negative charges that are going from one beaker to the other, or we have to have some positive charges that are coming the opposite direction to balance out the negative charges that are flowing that direction as well. Now the salt bridge is impermeable to the reagents, but it's permeable to counterions. Now batteries and fuel cells are examples of galvanic cells, or voltaic cells. Batteries have a static compartment containing the reactants. And once the reactants have been used up, the battery is then dead. It doesn't generate any more electricity. And so you can see there's a lot of different components inside our battery, but generally we have an electrode here. This one is the cathode. This one happens to be a carbon electrode. We then have a cap on our cell here. We can then connect that to a wire. We can have our load over here. In this case, it's just a generic light bulb. And that then has to be connected down to the other end of our battery. And in this case, it's then a zinc electrode. This is our anode. And in between our cathode here and our anode down there, in between there, we have this carbon and manganese dioxide mixture for this battery. Now let's look at an example of a fuel cell. We have down here a generic fuel cell. Fuel cells allow fresh reactants to flow past the electrodes. So you can see we've got some fuel coming in here. In this case, our fuel is hydrogen. And so the hydrogen flows in past this electrode here, and then is passed back out. That's the excess fuel. It then would get circulated back in until it gets used up. Now, some of those hydrogen molecules will lose some electrons. Those electrons can go out through some load and then come back in on the other side. Now, the hydrogen ions that were coming from that hydrogen molecule can then diffuse through this space. And then on the other side, those hydrogen ions will combine with some oxygen molecules that are coming in from air on this side. Those hydrogen ions will combine with the oxygen molecules to form some water molecules, and then water vapor goes out along with the unused air. Now, hydrogen fuel cells have been used by NASA and are used in some prototype cars because they output only this water vapor, and obviously the unused air that came in as well. But the only product from the reaction is going to be water vapor. And so they are an inherently clean type of energy source. Now, of course, you have to get this hydrogen from somewhere, and usually that would be produced in some other, perhaps not quite as clean power plant somewhere. Now, NASA uses these in their spacecraft because the hydrogen here is quite light. The oxygen is a good bit heavier than the hydrogen is, but it's still fairly light as far as elements are concerned. And this sort of energy source, a fuel cell, allows a lot of energy to be packed into a relatively small space, so a low volume, and a relatively low mass. Now let's examine a galvanic cell with two electrodes suspended in a solution of cadmium chloride. Now the cadmium here is cadmium 2+. Now one electrode is cadmium, that's this electrode here, and the other electrode is metallic silver covered with silver chloride. Now, at the cadmium electrode, this is the anode, we have oxidation occurring. That is, our cadmium metal is coming off of our anode. It's going into solution as cadmium 2+. Those electrons are then coming up the wire, in this case going through our potentiometer. They're coming down the other wire and into our silver electrode, where they are then combining with some of the silver ions from our silver chloride to form solid silver on that cathode. And again, the cathode is where the reduction is occurring. Now, the net reaction here looks something like this, where we have 2 silver chloride. In this case, it's in the solid phase because it's stuck onto the outside of our silver electrode. So our 2 silver chlorides are reacting with our solid cadmium to form 2 silver atoms. Note the charge here is 0, plus 2 chloride ions, plus our cadmium 2+ ion. Now we can split the overall reaction into 2 half reactions. Now the reduction half reaction is then the 2 silver chlorides are gaining 2 electrons to form 2 silver atoms and 2 chloride ions. And the oxidation half reaction is our cadmium solid is reacting to yield cadmium 2+ plus 2 electrons. And those 2 electrons are then the electrons that are going through that wire, our external circuit. Now, the oxidation of our cadmium to cadmium 2+ provides the electrons that are flowing through our external circuit. And those electrons arrive at our silver surface and reduce our silver ions from our silver chloride to metallic silver atoms with a charge of 0. And then the chloride goes into solution to balance out the charge from our cadmium 2+ ions that were forming at the other electrode. Now, the delta G for this reaction is minus 150 kilojoules per mole of cadmium. And this provides the driving force for pushing the electrons through our external circuit. Note that we have a negative value here, so we're getting energy out in our reaction. If we had a positive value, we would have to put energy in. That is, we would have to do work to drive this reaction to go. Now, obviously, if we reverse the reaction, and we're trying to get our metallic silver to ionize and go back and form our silver chloride, and then getting our cadmium to go back from our cadmium 2+ to our cadmium solid, if we were trying to get that reaction to go, we would have to put in 150 kilojoules per mole of our cadmium that we were forming in this case. Now let's suppose that we want to calculate the voltage produced by the cell that we described above. Remember that we have delta G is equal to minus NFE, and so we want to find the voltage, we want to find this E. So we can rearrange that to then E is equal to minus delta G over NF, and when we plug in our values, we then get down here a value of positive 0.777 volts. Now, note that a negative delta G gives a positive voltage. And recall that a negative delta G is a spontaneous reaction. And therefore, in a galvanic cell, a spontaneous reaction gives a positive voltage. So I've shown our battery here. We've got this positive end of our battery here, and the negative end of our battery is over there. Now, a non-spontaneous reaction will give a negative voltage. So if we flip our battery around, and we're trying to pass electrons instead of from the negative end around to the positive end, if we're trying to pass our electrons from the positive end around to the negative end, we're getting a negative voltage, which is then going to be a non-spontaneous reaction. So our electrons don't want to go from the positive side to the negative side. Right? They were repelled from the negative side, and they are attracted to the positive side of our battery. And then reactions at equilibrium will give us a 0 voltage. Because remember, if we have a reaction at equilibrium, our delta G is equal to 0. And that means that our voltage would then be equal to 0. And that means that we have a dead battery. We need to either charge it again, if it's a rechargeable battery, or we need to throw it away and replace it with a new one if it's an alkaline battery. Now, the electrode at which the reduction occurs is called the cathode. And the electrode at which the oxidation occurs is the anode. Now note that the electrical potential of the cathode is higher than that of the anode. That is, the cathode is positively charged and the anode is negatively charged. Now you can remember this if you remember that a cation is positively charged, and an anion is negatively charged. So a cathode is positively charged, and anode is negatively charged, just like the cation and anion. So if we look again at our schematic of our galvanic cell here, the reactions should then be at our cathode. We have our silver ions accepting the electrons to form our solid silver, and at the anode we have our cadmium giving up the electrons to form our cadmium 2+. And that means that our net reaction is then our 2 silver ions react with our solid cadmium to give us 2 solid silver ions plus our cadmium 2 ion. Now in this case, the overall reaction is spontaneous, but we won't get much current to flow through the external circuit. Now why not? The silver isn't forced to be reduced only at our silver electrode. In fact, it can react on the cadmium electrode directly. That is, we need to separate our silver ions from our cadmium electrode. Now we can separate the two reactants into two half cells by connecting them with our salt bridge here. Now the salt bridge is generally a U-shaped tube filled with a gel containing a large concentration of an electrolyte that does not affect the cell reaction, such as potassium nitrate. Now the ends of the salt bridge are capped with porous glass discs that allow ions to diffuse, but minimize the mixing of the solutions inside and outside the bridge. That is, we've got these porous glass discs down here, and those discs allow some of these ions to pass through, but minimize the intermixing of our cadmium nitrate on this side with our potassium nitrate inside there, and then on the other side with our silver nitrate and potassium nitrate. That is, we basically want to prevent our silver ions from going through the salt bridge and over here and reacting directly with our cadmium ions over here. Now, the migration of ions offsets the charge buildup that would otherwise occur as electrons flow from the anode over here to our cathode. Now, for most reactions that don't involve silver or other ions that will precipitate with chloride, then a potassium chloride salt bridge is used. And this salt bridge can be prepared by heating 3 grams of agar with 30 grams of potassium chloride in 100 milliliters of water until a clear solution is obtained, and then the solution is poured into our U-shaped tube and allowed to gel, and the bridge should then be stored in a saturated aqueous potassium chloride solution. Now, we will use a shorthand notation for electrochemical cells that involve 2 symbols. If we have one vertical line like this, that represents a phase boundary. So somewhere between, say, a solid phase and an aqueous phase, or between a gas phase and an aqueous phase, and so on. Now, a double vertical line like this represents the salt bridge, that U-shaped glass tube. So let's look at an example of this notation. We had, in our previous example, where we had our silver chloride reacting with our cadmium to form metallic silver and chloride and cadmium 2+ ions. Again, our anode was the cadmium electrode here. The electrons come out and pass over here to our silver cathode. Now, in our shorthand notation, we then write it like this. We have our cadmium solid, and that was then separated. There's this phase boundary, remember, because this is a solid phase, and our cadmium chloride here is in the aqueous phase, so we need that phase boundary. And now we have another phase boundary with our silver chloride, and that was in the solid phase as well. Over here, remember that was stuck onto the outside of our silver cathode. And then there's another phase boundary with the solid silver. Now remember, there's a phase boundary here because our cathode is solid silver, and then stuck to that we have our silver chloride. They're not mixed together, otherwise this phase boundary wouldn't be there. And note here that the electrons are shown at the far left, that's our cadmium solid over here, and the far right, that's our silver solid over here. Now, in another example, we then separated our cadmium solution from our silver solution, and we had a salt bridge. And remember, in this case now, again we have our cadmium electrode, symbolized here this way, and that then is this electrode here. And then we have this phase boundary with our cadmium nitrate, aqueous. So our cadmium nitrate is in here, in this beaker. And again, there's a phase boundary because this is in the aqueous phase, and our cadmium electrode was in the solid phase here. And now we've got this double line. That's then representing our salt bridge here. Now inside our salt bridge we've got potassium ions and nitrate ions, but you note we're not putting those in here because our salt bridge is simply acting as a way of carrying the charge. It's acting just like this wire is carrying charges. Right? Our wire is carrying electrical charges, our electrons from one side to the other, and our salt bridge is carrying some nitrate ions this way and some potassium ions that way to balance out our electrons that are moving through the wire. But it doesn't really matter what the identities of those charge carriers are. It doesn't matter that we have potassium ions and nitrate ions, so long as they don't react with any of the other species around. And so we have our salt bridge, and then we have our silver nitrate in solution. That's our aqueous phase here in the beaker. And another phase boundary, and then our silver solid, and that's our silver electrode here. So again, note that our two electrodes are all the way on the left. That's our cadmium electrode, and all the way on the right, our silver electrode. Now note that the reaction proceeds from the left side of our vertical line here to the right. That is, we have our cadmium solid turning into our cadmium ions, and we have our silver ions turning into solid silver. Just like up here in our reaction, where we have our reaction proceeding from left to right, we write out our shorthand notation with the reactions proceeding from left to right. Now, with our salt bridge, that then separates this into two half reactions. We have one half reaction on this side and one half reaction on that side. Now note that these are represented physically in the two separate beakers that we have, one on the left and one on the right. Now, the left side here with our cadmium represents the oxidation, while the right side over here with our silver represents the reduction half reaction. Now we can define the standard reduction potential, which we symbolize with this E0, as the potential difference of a reduction half cell with all the reactants and products at standard states. Now remember that standard states are, for solutes, an activity of 1, for gases, a fugacity of 1. Remember that fugacity is simply the gaseous version of activity. For solids, they're going to be the pure solid, and for liquids, they will be the pure liquid. So let's examine an example reaction, which we show down here. But we can't actually measure the potential difference of a half reaction. We need both oxidation and reduction to occur simultaneously. And that means that we need to pick a reference electrode to use. Now, the reference electrode that we've used is the standard hydrogen electrode, which we symbolize with this capital SHE. Now, the standard hydrogen electrode consists of a platinum electrode in contact with a solution in which the activity of hydrogen ions is 1, and in which the hydrogen gas is constantly bubbled to saturate the solution. Now the reaction at the surface of the platinum electrode then looks like this. We have our hydrogen ions that's in the aqueous phase with an activity of 1. They're gaining electrons to then form hydrogen gas with an activity or a fugacity of 1. Now when we write that out in our shorthand notation, we then get something that looks like this. We have our platinum solid, and then a phase boundary, because here we have a solid platinum, and here we have some gaseous hydrogen, and then we have another phase boundary, and we have aqueous hydrogen ions with an activity of 1. Now you'll note that in the chemical equation that we've written, we're going this way. We have our hydrogen ions turning into our hydrogen gas, but in the bottom one, we have it written the other way. Remember that in our shorthand notation, we're always showing the reaction proceeding from left to right. And that means that in the bottom one, it appears to be telling us that we have hydrogen gas turning into hydrogen ions. Now, that's because we've actually written our chemical reaction backwards. What we really have in this case is we have hydrogen gas that is losing an electron to give us a hydrogen ion. Now, because this is our reference electrode, we're going to arbitrarily assign a potential of 0 to this electrode, our standard hydrogen electrode, at 25 degrees C. Now it doesn't actually matter what potential we assign this electrode because we're interested in differences in potential between this electrode and other electrodes. For example, if we assign the potential of this electrode to 200 volts, then the potential of all the other electrodes would simply shift up by 200 volts as well. But bear in mind that the potential difference would remain the same. And thus, if we're going to arbitrarily assign a value, we might as well arbitrarily assign a 0 to this. Now this means that any potential difference measured between the saturated hydrogen electrode and another electrode can be assigned to the other electrode. And thus, the plus 0.799 volts that was measured can be assigned to the standard reduction potential for this cell, that is, for our silver ions reacting to silver solid. And if we write out the line notation for the reaction that we have going on down here in our schematic, is given here. We have our saturated hydrogen electrode on the left, then we have our salt bridge here, and then we have our aqueous silver ions. There should be a charge on this, +1 up there. Our aqueous silver ions are reacting to give us our solid silver. Now, we can take this left part over here and symbolize it all with one short notation here, SHE, for the standard hydrogen electrode. So anytime you see this, it really means that whole stuff. Our saturated hydrogen electrode, which is basically everything on the left side here of our diagram. And that way we can shorten this and just show what we have on the right, plus this saturated hydrogen electrode on the left. Now, by convention, the platinum electrode from the standard hydrogen electrode is attached to the negative, the reference terminal of our potentiometer, and the right-hand electrode is attached to the positive terminal. Now suppose that we want to measure the standard reduction potential of the half reaction given here, where we had our cadmium-2 reacting with 2 electrons to give us our cadmium solid. So we can construct our cell with a saturated hydrogen electrode, a salt bridge, and then our cadmium aqueous with an activity of 1, reacting to give us our solid cadmium. And in this case, we would measure a potential difference of negative 0.402 volts. And this means that the electrons are flowing from our cadmium electrode to our platinum electrode. That is, the electrons are going this direction. Now, by measuring the potential differences for a large number of half reactions with respect to the standard hydrogen electrode, we can then construct a table looks something like this of the oxidizing power of various species. And note that there's a much larger table in the back of the book, in one of the appendices, listing out all of these E0 values for a bunch of different reactions in here. Now, if we increase the reactant concentrations, then Le Chatelier's principle tells us that we should drive the reaction to the right. Now, the net driving force for a redox reaction is expressed by what we call the Nernst equation. Now, the Nernst equation has a term including the driving force under standard conditions, E0, which applies if all the activities are 1, and a term including the dependence on reagent concentrations in the form of activities. So what does it look like? Well, for the generic half reaction given here, where we have A moles of A reactant plus N electrons, reacting to give us B moles of B, our product, then the Nernst equation given by the half cell potential, which we're going to symbolize a capital E, is then shown here, where again this E0 is our standard reduction potential when all the activities are 1. R here is the gas constant, just like in PV equals nRT. T here is the temperature in Kelvin. N is the number of electrons in the half reaction, that's this N up here. And F here is the Faraday constant, and then the A sub I, so either the A here or the A B there, is the activity. So this term here is the activity of A, this guy, and the AB here is the activity of B, this guy, and then they are raised to the little a or little b, the coefficients up here in our reaction. Now, that fraction in the logarithm is the reaction quotient, which is Q. So Q is equal to this term, the activity for B raised to the little b power, divided by the activity for A raised to the little a power. Now Q has the same form as the equilibrium constant K, but the activities are not confined to be at the equilibrium values. Now remember that pure solids, pure liquids, and solvents are omitted because their activities are always 1, or for solvents they're very close to 1. Now the concentrations of solutes are expressed in molarity, and the concentrations of gases are expressed in bars. And if all activities are 1, then Q equals 1, and thus the natural log of Q equals 0, and that means that E is equal to E naught. That is, the cell potential is equal to the standard cell potential. Which of course makes sense, because if all of the activities are 1, then everything is at its standard state, and that means that the cell potential should be equal to the standard cell potential. Now we can convert the base of the logarithm from base E to base 10, fix the temperature to 298.15 Kelvin, that is 25 degrees C, and plug in the values of constants to give us the Nernst equation at 25 degrees C, that is given here. So we have E, our cell potential, is equal to E naught minus 0.05916 volts divided by N, remember N is our number of electrons transferred, times log, this is now log base 10, of Q. And note that we can now see that the potential difference changes by 59.16 divided by N millivolts for an order of magnitude change in Q. So let's look at an example. The Nernst equation for the reduction of white phosphorus to phosphine gas is given here. We have our white phosphorus reacting with hydrogen ions. They're gaining 3 electrons. We're forming our phosphine gas. The standard reduction potential here is minus 0.046 volts. So we can plug in for our E naught, we can plug in our minus 0.046 volts. And then for our N, we're plugging in 3 because we're transferring 3 electrons. And that's then multiplied by this log of Q term, where we have the pressure of phosphine gas, that's our pH 3 up here, and then divided by the cube of our hydrogen ion concentration. Now if we multiply the half reaction by a factor, then E naught does not change, but N and Q do change. For example, if we multiply the last example by 2, then our 1/4 of our white phosphorus becomes 1/2, and now we'll have 2 phosphorus atoms involved. We'll have 6 hydrogen ions, 6 electrons, and we'll form 2 of our phosphine gas molecules. And that means that our E naught still hasn't changed, but now our N has gone from 3 to 6, and that means that over here we have, instead of our pressure of phosphine raised to the first power, now it's raised to the second power. We've got it squared. And for our hydrogen ion concentration, instead of being raised to the third power, it's now raised to the 6th power. And so now we want to see, has the cell potential changed? Has E changed? So we want to know whether or not our two E values are equal. So what we want to know is this. We want to know, is E1 equal to E2? Well, so let's set them equal to each other and then test whether or not that is true. So we have our negative 0.046 volts minus 0.05916 volts divided by 3 times log of our Q value in the first case is equal to that same minus 0.046 volts minus 0.05916 volts divided by 6 times our log and then our Q term in the second case. Now, of course, this term here is going to cancel with this term there, and our 0.0596 volts is going to cancel with this 0.0596 volts here. And that then leaves us with this 1/3 term here, which we've got there, and the 1/6 term here, and then we have our logarithm and our Q there and our Q term here. Well, if we leave the left side the same, and then on the right side, if we take this term and we factor out this Q that we have, remember that this term is simply this term over here squared, and so we end up with the same value here as we have here, and now we're just squaring it on this side. And remember that log of x to the y is equal to y times log of x. And that means that on our second term on the right side there, in our logarithm term, we can take that squared out and move it out here in front. And then we have this 2 times 1/6, and that's then 2/6 or 1/3. And now we have the same thing on the left as we have on the right. And that then proves that the value of E, our cell potential, does not change if we multiply the reaction by some factor. Now, for a complete reaction, the potential difference is the difference between the potentials of the two electrodes. That is, the E here, this is the E for the entire cell, not just one half cell, is equal to E plus minus E minus. That is, the E plus here is the potential difference of the electrode attached to the positive terminal of the potentiometer, and the E minus term here is the potential of the electrode attached to the negative terminal. Now, the potential of each half reaction, written in the form of a reduction reaction, is governed by a Nernst equation, and the voltage for the complete reaction is the difference between the potential of the two half cells. Now, the procedure for writing a net cell reaction and finding its voltage is then given here. First, we write the reduction half reactions for both half cells, and then find E0 for each in appendix H. Remember, this is a table of reduction potentials, similar to that table that I showed earlier. We then multiply the half reactions as necessary so they both contain the same number of electrons. Now remember that you do not multiply E0. And then we write a Nernst equation for the right half cell, and this is the half cell connected to the positive terminal of our potentiometer, so this is our E plus. Next, we write a Nernst equation for our left half cell, and this is the half cell connected to the negative terminal of our potentiometer, so this is E minus. And now we have our E plus and we have our E minus. We subtract E minus from E plus, and that gives us our overall E, which is sometimes written as E cell. So we then write the net cell reaction by subtracting the left half reaction from the right half reaction, and note that the subtraction in a chemical reaction is the same as adding the reverse reaction. In other words, instead of subtracting the reduction, we can add the oxidation reaction. Now, if E is positive, then the net cell reaction is spontaneous in the forward direction. That is, electrons will flow from the left cell to the right cell. On the other hand, if E is negative, then the net cell reaction is spontaneous in the reverse direction. That is, electrons will flow from the right cell to the left cell. Now, let's find the voltage of the reduction of silver ions with cadmium if we use 0.5 molar silver nitrate and 0.1 molar cadmium nitrate. The right electrode is then our silver ions gaining electrons to give us solid silver, and we know that the E0 there is plus 0.799 volts, and this is then going to be our E0 plus. The left electrode is then our cadmium 2 ions reacting with our 2 electrons to give us solid cadmium, and the E0 there is negative 0.402 volts, and this is then our E0 negative. Now the Nernst equation for the left electrode is then given here. We have our E0 plus minus 0.05916 volts divided by 2, because we're transferring 2 electrons, times the log of 1 over the square of our silver ion concentration. Our silver ion concentration is then 0.5 molar, so when we square that and we work out the rest of the math, we get a value of plus 0.781 volts. And the Nernst equation for the right electrode is then E0 minus 0.05916 volts divided by 2, again we're transferring 2 electrons, times log of 1 over the cadmium ion concentration. When we plug in the cadmium ion concentration of 0.01 molar, then we get an E minus of minus 0.461 volts. And the overall cell voltage, our overall E or E cell, is equal to our E plus, which was 0.781 volts, minus our E minus, which was then minus a negative 0.461 volts, which then gives us an overall value of positive 1.242 volts. Now when we write the net cell reaction, we have our reduction reaction, where we have our silver being reduced to solid silver, minus then our oxidation reaction, which again written here is written as the reduction reaction, which then is the same thing as plus our oxidation reaction, and that then gives us our overall reaction down here. Now again, the cell voltage is positive, and so the reaction is spontaneous in the forward direction. That is, the cadmium solid is oxidized to cadmium ions, and the silver ions are reduced to solid silver. And that means that the electrons flow from our left electrode to the right electrode. Now in our last example, we found that E for the silver half cell was 0.781 volts, and E for the cadmium half cell was minus 0.461 volts. And let's go ahead and place these values on a number line. So we have our negative 0.461 volts here for our cadmium reaction, and we have the positive 0.781 volts here for our silver reaction. And if we look at the difference between those two, we have this value of 1.242 volts. We have an electrical potential difference of 1.242 volts from our cadmium electrode to our silver electrode. Now remember that electrons always flow toward the more positive potential because the electrons are negatively charged, and thus they're attracted to our positively charged particles. And note that this is going to be true even if both half cell potentials are negative or if both of them are positive. The electrons will always be flowing in this direction. And again, if we return to one of our earlier examples, in our example of the reduction of our silver chloride with cadmium, then the right half reaction can be written like this, and we have then an E naught plus of 0.222 volts. And we can then plug in our chloride ion concentration in here, our 0.0334 molar, and that gives us a value here for our E plus of 0.309 volts. Now note that the chloride ion concentration for this reaction comes from our cadmium chloride concentration. Our cadmium chloride concentration was 0.0167 molar, and then because we have two chlorides there for every cadmium chloride, we had to double that value. That's giving us our 0.0334 molar. Now suppose we instead wrote the half reaction like this. And this is then going to give us an E naught plus of plus 0.799 volts. Now this is just as valid a description as the other description because in both cases our silver ion is reduced to silver 0. Now if they're both equally valid, then they should both give us the same voltage for our cell potential. Now the Nernst equation for this half reaction looks like this. We have our plus 0.0799 volts, and now we need to plug in our silver ion concentration here. So now the question is, what is our silver ion concentration? Well, we have solid silver chloride, and that means that we can use the solubility product and the chloride ion concentration to find the concentration of silver ions. That is, we have our KSP. In this case, we know the value is 1.8 times 10 to the minus 10. We know our chloride ion concentration, so we can solve this equation for our silver ion concentration. That's then equal to our KSP value divided by our chloride ion concentration, so 1.8 times 10 to the minus 10 divided by 0.0334. And that gives us a silver ion concentration of 5.4 times 10 to the minus 9 molar. Now plugging this into the Nernst equation then gives us this equation where again we've plugged in our silver ion concentration here, and when we work out the math we get 0.309 volts. Now this value is nearly the same as the 0.0309 volts we calculated earlier, and note here that we have a slight difference in this subscripted number that's basically past our number of sig figs. And that difference arises from the accuracy of our KSP value and the fact that we ignored the activity coefficients. That is, both calculations give essentially the same potential difference because they both describe the same chemistry, just in slightly different ways. And therefore, it doesn't matter if you write your cell potential slightly differently than I do. That is, if you say include the chloride ion and I don't include the chloride ion, we are going to end up with at least almost exactly the same value. Now, if you need to write half reactions given the line notation or cell drawing, first look for an element in two different oxidation states. For example, if we're given this line notation, we know, of course, we have a salt bridge and we have a number of places where the phase is changing. Now, we see lead in two different oxidation states. We see lead over here as lead 0 and here as lead 2. And then we see copper here as copper 2 and as copper 0. Now the half reactions involved then are our copper 2 plus, gaining a couple of electrons to form our copper solid, our copper 0. And we then have our lead fluoride, gaining 2 electrons, where the lead charge is then going from a +2 over here to a 0 over here. And our fluoride ions are simply along for the ride. Now note that we could have written the second reaction like this, and we've already shown that we would then get the same end result for our half cell potential. So it doesn't matter whether we write our equation this way or like this. Now note that we know that if there is solid lead fluoride, then some of our lead ion is present in solution due to the dissolution equilibrium, due to our KSP expression. And which reaction we pick to use depends on whether the fluoride ion concentration or the lead ion concentration is easier to determine. Now note that we can't write the left-hand cell as a redox reaction involving fluorine like this. Now we can't write such a reaction because fluorine does not exist in two different oxidation states in the cell. We have fluoride here, but we also have fluoride there. Remember that in lead fluoride, the fluoride here has a charge of 1-. And that means that we don't have this species around. We only have our fluoride around. We don't have fluorine in a different oxidation state. Now we know that a galvanic cell produces electricity because it is not at equilibrium. When we connect a potentiometer, aren't we allowing current to flow and thus changing the reactant and product concentrations and thereby the voltage? Well, the resistance of a good quality potentiometer is on the order of 10 to the 13 ohms, and that means that the current flow is negligibly small. So let's examine a generic galvanic cell, where we have, at the right electrode, we have A moles of A reacting with N electrons to give us C moles of C, and this then is our E0 plus, because it's our right electrode. And at the left electrode, we have D moles of D reacting with N moles of electrons to give us B moles of B, and this is then our E0 minus. Now note here that at our left electrode, we're later going to end up switching this, so our B would basically be on the left side and our D will be on the right. So A and B are in fact our reactants and C and D are our products in the overall reaction. That is, down here we've got our overall reaction. We have A moles of A plus B moles of B react to C moles of C and D moles of D. Now remember, our right-hand electrode, we are writing down here in the forward direction. Our left-hand electrode, which we've written here as a reduction, is actually occurring as an oxidation, and that means that we're flipping it around, and so we have our B reacting to give us D. Now the Nernst equation is then given here. So remember, for each half cell, we're going to have an equation that looks like this, where we have our E0, so we have either our E0 plus or our E0 minus, and then minus the RT over NF times natural log of our Q value. Now when we've converted from our natural log to our log base 10, that then gives us this fraction here. And so if we leave in our n term here, we then have our E naught plus minus that fraction with our n, log of this term, minus E naught minus this term, and then log of this Q. And we can then group together our standard cell potentials, our E naughts, together here. And then we can group together this term here and this term here into one big term, because the n here and the n there will be the same value, and so that will be just a single n here. And then we have one log term where we have our activity of C and our activity of D on the top, and our activity of A and activity of B on the bottom. Now note that this term here is then simply Q, the reaction quotient for the overall reaction, and this term over here, this first term in parentheses, is simply E naught for the entire cell. Now note that Harris denotes the standard cell potential as E naught, but I'm here denoting it as E naught cell for clarity. It's not E naught of either of our two half reactions, it's E naught for the entire cell. Now in the special case that the reaction is at equilibrium at 25 degrees C, in that case then Q is equal to K, and we know that E is equal to 0. And because, remember, this is what we had on the last slide, then we have, when we plug in our 0 here for E, and we plug in our K for Q there, we then get 0 is equal to E naught cell minus 0.05916 divided by n times log of K. And if we then take this term and move it to the other side, we then have E naught cell is equal to 0.05916 divided by n times log of K. And if we then solve this for K, we get K, our equilibrium constant, is equal to 10 raised to the n times E cell naught divided by 0.05916. And now we can use electrochemistry to determine equilibrium constants. So let's look at an example. If we have solid copper reacting with iron 3 to form iron 2 and copper 2, we can then divide the reaction into two half reactions that we know the standard potential for. So again, see Appendix H for where I'm getting these values from. For our overall reaction here, we then have an E cell naught of 0.432 volts. And we can then find K by plugging in our 0.432 volts here, plugging in our 2 electrons that are transferred there, that was our N value. And that gives us a K, an equilibrium constant of 4 times 10 to the 14. So let's look at another example. In this case, we now have iron carbonate being reduced. So our iron is iron 2 being reduced to iron 0, elemental iron. We still have our carbonate left over. The E naught plus there is negative 0.756 volts. And then we also have our iron 2 plus being reduced to solid iron. There we have an E naught minus of negative 0.44 volts. Now note here that really this reaction is occurring the other way. We have our solid iron going to iron 2. And that means that our overall reaction then is our solid iron carbonate is reacting to give us iron 2 plus carbonate. And our E naught cell there is then going to be negative 0.31 volts. Now we can then find our K, and note here that our K is a special K. This is a KSP because we have simply our solid iron carbonate turning into iron 2 ions and carbonate ions. And so here the value then is 10 to the negative 11th. But remember here, the overall reaction is not a redox reaction. So how can we have a redox potential if we don't in fact have a redox reaction? Well, remember that delta G was equal to negative NFE. So E is simply another way of expressing the free energy change of our reaction. Now, when we're dealing with galvanic cells, we have two types of equilibrium to be concerned with. Equilibrium between the two half cells and equilibrium within a half cell. Now, so long as the cell has a non-zero voltage, that is, E is not equal to 0, then the net cell reaction is not at equilibrium. That is, there is no equilibrium between the two half cells, between this side and that side. Now, within the half cell, we can then allow any relevant reactions to reach equilibrium. If we have the cell depicted to the right here, we then have a reaction occurring in the right half cell over here that looks like this. We have our solid silver chloride that's plating our silver electrode, reacting to yield silver ions and chloride ions. Now, this equilibrium is not part of our net cell reaction. It occurs whenever the silver chloride is in contact with water. Now, the left half cell has another equilibrium. It has the acid dissociation reaction for our acetic acid. And this equilibrium is also not a part of the net cell reaction, but it occurs whenever acetic acid, or the acetate ion here, is in contact with water. So let's write the half reactions for this cell. The right half reaction is given here. We have our silver chloride solid, gaining an electron to give us solid silver, and a chloride ion. In this case, our chloride ion has a concentration of 0.1 molar, and that then gives us an E0 plus of plus 0.222 volts. Now the line notation for the left half reaction then looks like this, where we have our solid platinum, we have our hydrogen gas here with a pressure of 1 bar, we have then our acetic acid with a concentration of 0.05 molar, and our sodium acetate with a concentration of 0.005 molar. And again, because we have a weak acid and its conjugate weak base, we have a buffer solution there. And that means that our left half reaction looks something like this, where we have our hydrogen ions at some unspecified concentration, gaining electrons to give us hydrogen gas, which we know the concentration of. We know the fugacity there is 1 bar. And remember that E0 minus here is going to be 0 volts because we've defined it that way, because this electrode here is the standard hydrogen electrode. But we don't know our hydrogen ion concentration. Now the Nernst equation for this cell is then given here, and when we plug in our values here for 1 electron being transferred, in this case we plug in for our E0 plus our 0.222 volts, we plug in for our chloride concentration our 0.1 volts, we plug in for our hydrogen electrode, our E0 minus there, we plug in 0, plug in 2 electrons here, we plug in our pressure for our hydrogen gas there of 1 bar, and then we're only left with our square of our hydrogen ion concentration down here. And we can now relate our E cell to the hydrogen ion concentration, and therefore to pH. So we have essentially made a pH meter. But wait, we know from the figure that E cell was equal to plus 0.503 volts. And that means that from our plus 0.503 volts, when we plug in our values, we can then solve for our hydrogen ion concentration, and we get a value of 1.8 times 10 to the minus 4 molar. Now, using the hydrogen ion concentration, the acetic acid concentration, and the acetate concentration, we can now calculate the acid dissociation constant for our acetic acid. We can plug in 0.0050 for our acetate ion concentration. We can plug in 1.8 times 10 to the minus 4 molar for our hydrogen ion concentration, and we can plug in 0.050 molar for our acetic acid concentration, and that gives us a Ka value of 1.8 times 10 to the minus 5 molar. And thus, we can use electrochemistry to measure concentrations and equilibrium constants that might otherwise be too difficult for us to measure. So let's look at some survival tips. In Harris's words, problems in this chapter include some brain busters designed to bring together your knowledge of electrochemistry, chemical equilibrium, solubility, complex formation, and acid-base chemistry. They require you to find the equilibrium constant for a reaction that occurs in only one half cell. The reaction of interest is not the net cell reaction and is not a redox reaction. He then suggests the following approach. First, write the two half reactions and their standard reduction potentials, and if you happen to have chosen a half reaction for which you cannot find E0, then find another way to write the reaction for which you can find E0. Next, write a Nernst equation for the net reaction and put in all the known quantities, and hopefully there will be only one unknown. Then, solve for the unknown concentration, and use that concentration to solve the chemical equilibrium problem that was originally posed. For example, the cell to the right here measures the formation constant Kf of our mercury EDTA complex. And suppose we want to find the value of Kf. So we're given a few things. We know the cell voltage here is plus 0.342 volts. We know on the left-hand side we have our standard hydrogen electrode, and on the right-hand side we have 50 milliliters of 0.01 molar mercury chloride, 40 milliliters of 0.05 molar EDTA, 10 milliliters of a buffer with a pH of 6, so we'll know the hydrogen ion concentration. Now, the left half cell is our standard hydrogen electrode, and that means that E minus is 0 volts. And in the right half cell, the half reaction looks like this. We have our mercury 2 ions being reduced to our mercury 0, and that gives us an E0 plus of 0.852 volts. And the Nernst equation then looks something like this, where we have our plus 0.852 volts minus 0.05916 divided by 2 times log of the inverse of the mercury 2 concentration. And in the right half cell, we also have the equilibrium between mercury 2 and EDTA. Now, we're going to symbolize the EDTA here as Y4 minus to be the free EDTA. This is our fully deprotonated EDTA. So our formation reaction here, where we are adding our mercury 2 ion to our EDTA to give us our mercury EDTA complex, that then has a Kf value, and this is the value we're trying to find. Now we expect Kf to be large, so let's assume that all of our mercury 2 reacts to form mercury EDTA complex. Now we had 50 milliliters of 0.01 molar mercury chloride, so the moles of mercury ion are then 5 times 10 to the minus 4 molar. And the total volume is 100 milliliters, and that means that our mercury EDTA complex concentration is then 5 times 10 to the minus 3 molar. And the remaining EDTA has a total concentration given here, where we have our 40 milliliters of EDTA converted into liters, and then times our initial concentration of our EDTA in that 40 milliliters, and that gives us 2 times 10 to the minus 3 moles of EDTA at the start. Now, we know that we have reacted away 5 times 10 to the minus 4 moles of EDTA, and that means that 1.50 times 10 to the minus 3 moles of EDTA remain. And now that 1.50 moles of EDTA divided by now our volume of 100 milliliters, converting that volume from milliliters to liters, then gives us an EDTA concentration of 1.5 times 10 to the minus 2 molar. Now the formation constant is then Kf is equal to the mercury EDTA complex concentration divided by the mercury 2 concentration times the EDTA concentration. And this concentration here is the fully deprotonated form of our EDTA, our uncomplexed form. Now we can replace that with these two terms over here, our total EDTA concentration that is not bound to our mercury ions, and then this alpha Y4 minus is then the fraction of our total EDTA, so the fraction of this guy, in the Y minus form. And we now know all of the values except for our Kf here and for our mercury 2 concentration. Now the Nernst equation for the net cell reaction is given here. We know that that value is plus 0.342, and that has to be equal to E plus minus E minus. Now, we know that E minus is 0 because that's the standard hydrogen electrode, and that means that this plus 0.342 value has to be equal to this term in parentheses, and we know that that then is plus 0.852 minus 0.05916 over 2 times log of the inverse of the mercury ion concentration. And that means when we solve for this guy, we get a value of 5.7 times 10 to the minus 18 molar. And now we can plug that value in here. We can plug in our 5.7 times 10 to the minus 18 molar for our mercury ion concentration. We can plug in our 0.005 molar concentration for our mercury EDTA complex. We can plug in our fraction here as 1.8 times 10 to the minus 5, and we can plug in our total EDTA concentration of 1.5 times 10 to the minus 3 molar. And that gives us a Kf of 3 times 10 to the 21. Now note that the mixture of EDTA and our mercury EDTA complex serves as a buffer of sorts for our mercury 2 ion and fixes its concentration. And then our mercury 2 ion concentration determines the cell potential for our overall cell. Now, the standard reduction potentials that we have discussed thus far, these are these E naughts, are for the case where all reactants and products have activities of 1. Now, if hydrogen ion is involved, that means that the pH equals 0. And if hydrogen ions, hydroxide ions, or if an acid or base is involved in the redox reaction, then the reduction potential will depend upon the pH. Now, most biological environments have a pH far closer to pH of 7 than to pH of 0, and thus the standard reduction potentials we have been using are not particularly appropriate for use in biological environments. So instead of using the standard reduction potentials, let's use a formal reduction potential. A formal reduction potential is the reduction potential that applies under a specified set of conditions, that is, pH, ionic strength, concentration of complexing agents, and so on. The formal potential at pH equal to 7 is called E0 prime or E0 prime. Now let's examine the half reaction shown here. We have A moles of A reacting with N moles of electrons to give us B moles of B and M moles of hydrogen ions. And we have our E0 here, where A here represents some oxidized species and B represents some reduced species. Now note here that A and B may also be acids or bases. Now the Nernst equation for the half reaction then is given here, where we have E is equal to E0 minus 0.05916 over N times log of B concentration raised to the B power times the hydrogen ion concentration raised to the M power times the A concentration raised to the A power. Now if we want to find E0 prime, then we can rearrange the Nernst equation to a form in which the log term includes only this FA term and FB term, where F then is the formal concentration of a species. So this term here, this FA term, is the formal concentration of A, and this term is the formal concentration of B, and each of them are then raised to the little a and the little b powers, respectively. So we then have our E is equal to this E0 prime, where we've grouped together our E0 plus some other terms, and this is E0 prime if we have a pH of 7, and then minus 0.05916 over N times log of our formal concentrations of B and A raised to the little b and little a powers. Now to find our formal concentrations, we use the fractional composition equations that we've derived earlier in section 9.5. For monoprotic systems, we have the concentration of our protonated form is equal to our alpha HA times F, which is then equal to the hydrogen ion concentration times F divided by Ka plus the hydrogen ion concentration. And for our A minus, our conjugate base concentration, we have alpha A minus times F, which is equal to Ka times F divided by the hydrogen ion concentration plus Ka. For the diprotic systems, we then have three equations, one for our doubly protonated form, one for our doubly deprotonated form, and one for our intermediate form. And we can measure our E0 prime by making a half cell in which the formal concentrations of the oxidized and reduced species are equal, and the pH is equal to 7. And the log term is then 0, and the measured potential versus the saturated hydrogen electrode is then our E0 prime value.